Roscoe here at the University of Montana, a video lecture on 8-4 prime numbers for our Math 234 Math for Elementary School Teachers. We've already started this topic in class on Wednesday, so this is just to finish this off. And where have we been? So far we've taken a look at the first three of these bullets. We know what primes and composites are. We've talked about finding them using a process known as the sieve of Eratosthenes. And we've talked a little bit about determining how we can determine if, let's say, a given three-digit number is prime or composite through trial division up to the square root. So let's move on and talk a little bit about prime factorizations, the fourth topic in our list here. So here's where we are. So let's take a look at the prime factorization process using two different methods. One is called a factor tree. It's definitely the dominant method that's taught by most teachers, I think, when we find prime factorizations of a number. So I'll switch over to my document camera and we'll take a look at 336 and how we might find its prime factorization using a factor tree. So probably you were taught somewhere along the line that you can break things down into factors by thinking them as a factor tree. So 336, for example, can be thought of as 2 times some number. I know it's even, so I'll go ahead and divide it by 2. And I get 168. Well, let's see. So I notice 68 is divisible by 4, so I should be able to break that down by 4. So it does indeed break down 4 and 2. Now 2 itself is prime, so I guess I'm done at that stage. I can't go any further other than to write 2 and 1 isn't a prime number, so I would leave it at 2. But both of these numbers, 4 and 42, are composites, so I would break this one down into its product of 2 times 2, and 42 I can break down into a product, why don't I say 6 times 7. So it looks like 7 is prime. We've got 2 2s, 3 2s. Those are all prime, but 6 is a composite number, which can be broken down into 2 times 3. So I guess we've gotten as far as we can. And so what we would do at this point is gather all of these prime ends, I guess, of the factor tree. And notice that what we get is, let's see. 1, 2, 3, 4 powers of 2, 1 power of 3, and 1 power of 7. So if we wanted to write 336 as a product of primes, or in its prime factorization, we could write it as 2 raised to the 4th times 3 times 7. And of course, this order doesn't matter. I just wrote it smallest to largest, but we're in a multiplicative setting, and multiplication is commutative, so we could have chosen to put the 7 or the 3 first if we wanted to. But there's a prime factorization for 336. One thing I want to make sure and impress upon you is the fact that this prime factorization is unique. In other words, there is one and only one prime factorization for 336 up to order. In other words, the order could be different, but the members will be the same. To make sure that that's apparent to you, I'd like to just do another factor tree for 336. Oops. Say, I use my divisibility test for 4 right off the bat, and I saw that 36 is divisible by 4, so the number should be divisible by 4. So what if I went 4 and, well, what does 336 divided by 4 give us? Let's find out. It gives us 84. Okay, well, my 4 then can be broken down into 2 times 2, and certainly this one is divisible by 4 because the last 2 digits are divisible by 4, and that's a 21. And then the 4 here can break down into a 2 and a 2, and the 21 can break down into a 3 and a 7. And so what do we notice? Well, if we gather the ends of our factor tree, I've got 4 2s, a 3, and a 7. So this factor tree is showing me that 336 is equal to 2 to the 4th times 3 times 7, which I don't know if you noticed this, but of course the factor tree looks very different here because I started with a 2 and a 168. Here I started with a 4 and an 84. Well, what's important for you to realize is that this prime factorization is unique. In other words, we get to the exact same spot in terms of the final factorization in prime forms. So that's a real powerful tool, and we'll see in a bit what that gives us. One thing I want to make sure you're aware of is that in recent years, there's been a growing use of a new prime factorization method called factor lattice. And let's go ahead and do 336 using a factor lattice just to contrast this method. So once again, we already know what 336 prime factorization is, so we should get the exact same prime factorization, 2 to the 4th times 3 times 7. So how does a factor lattice differ? How does that look different? Grab my eraser. So a factor lattice takes 336 as the first, I guess, piece on the lattice. And what it does is it says, okay, well, try to divide it by the smallest prime. So if I get my sheet out, I remember that the smallest prime is 2, so I'll take a factor of 2 out of it. When I take a factor of 2 out of 336, I get 168, right? And then continue to take as many of these small factors as you can until you can't anymore. So I'll take 2 out again and I'll get, what, 84? I'll take 2 out again and I'll get 42. I'll take 2 out again and I'll get 21. And at this point, I know that I've exhausted all the 2's that I can take out of 336. It can be divided by 2 exactly 4 times because the end result is an odd number. So then what you do is you go to the next smallest prime, which is 3, and try it next. So does 21 divide by 3? Well, 2 plus 1 is 3. 3 is divisible by 3, so certainly 21 is divisible by 3. It's 3, it's 7, sorry. Divided by 3 is 7. And then I work my way up until I get a 1 here, and I know that the only thing that I can divide 7 by is 7 itself. So I divide 7 by 7 and I get 1. So this idea of a factor lattice is one method that's been, I guess, growing in popularity because what's left on the left-hand side is, of course, the prime factorization of the number written in sort of vertical form. So that means that 336 must be equal to 2 to the 4th times 3 times 7, because when I divide it by 4 2's, a 3 and a 7, I get a 1, right? So this times that equals 336. Interestingly enough, too, I don't know if you noticed this, but any place you make an L, 2 times 2 times 2 times 42 will give me 336. 2 times 2 times 2 times 2 times 21 will give me 336. 2 times 2 times 2 times 2 times 3 times 7 will give you. So any place you make an L, you find a product, but it's the one on the left-hand side when we get to 1 that's composed of all prime numbers that is the actual prime factorization of the number. So that's the lattice method. One of its advantages over the factor tree method is that the gathering of the factors doesn't depend on the uniqueness of the trees. It's always in this left-hand column. We see kids sometimes miss a 2 because it's higher up on the tree in the factor tree method. So in terms of increasing student proficiency, the lattice method tends to be a little bit better. It's also the dominant method that's taught in Europe for constructing prime factorizations. Okay, one thing I want you to think about now is, well, what's the point? I mean, why do we do this prime factorization other than to show that we can kind of reverse multiplication into these prime products? And I want you to try this right now and see what happens. And then come back and watch, I guess, the second part of the video. So why don't you go ahead and pause right here and give this a try. What I want you to do is find the prime factorization of the number 72. And then what I want you to do is find all the factors of 72. So what are the numbers that divide 72 evenly? And then from all of those factors, would you find each of those factors prime factorization? And then ask this question: how are the prime factorization of a number and the prime factorization of its factors related? Okay, I'm going to go ahead and stop there. Would you please do that investigation and then watch the second half of this video?